This is the screencast for section 3.2, example 3. Well, I told you it was coming. Now your calculator is not going to be as awesome as you thought it was, but you know what? Nobody's perfect. So your calculator, I mentioned in the last example, takes a specific h value, but it does more. It uses this h value of 0.0000001. And the reason why it uses a specific h value instead of doing all the function processing and canceling out using the symmetric difference quotient like you've been using is because that's way too much for a calculator or a little computer to do. So it takes a specific h value and uses a method as an estimate. Now the estimate is usually pretty accurate, but as you saw in example 2, it's not always perfect. What it does is it takes this h value, very, very tiny, and it adds it on to the a value that you want to find the derivative of and subtracts it from the a value you want to find the derivative of. Then it uses those 2 points to calculate the slope. So as you can see here, this slope is going to be different than this slope here. Now it's a better estimate than using our point at the spot of the derivative and just another point, because that's a little bit more crooked. So we have a better chance of getting an accurate estimate using the symmetric difference quotient, and that process is up here. Now if you're a little overwhelmed by all these different limits as things approach things, on this next page of notes here, I broke down each of the 3 of these and their purpose, their formulas, and a picture of what they're doing. So maybe you want to take a couple minutes, look over those, and that'll help you clarify the difference between the definition of derivative, the alternate definition of a derivative, and the symmetric difference quotient. So though the symmetric difference quotient is a good estimate if you use a small enough h value, it does have some flaws. For example here, if we're going to find the derivative of the absolute value at 0, we know from our previous examples that that's a corner and there's going to be no derivative there. The limit of the slopes from the left do not equal the limit of the slopes from the right. So we know that's going to be undefined. However, if you go math 8 or math derive in your calculator and evaluate that at 0, your calculator comes out with the number 0. It does not say error. It does not say undefined. Be very careful of this. What your calculator does is it takes a little a minus h and a plus h, finds those 2 values, those 2 points, and calculates the slope, so it thinks the slope is 0. That is a big time calculator fail. So it's up to us to be smarter than the calculator is and know when your calculator is producing a correct derivative as opposed to not. Then now try problem number 23, says find the numerical derivative of the given function at the indicated point. And it's telling us to use h equals 0.001, but I want us to use the calculator. And then we're going to identify if the function is differentiable at that point. Well, let's look at the calculator first. And my calculator tells me that the derivative of x to the 2/3 for x equals 0, at x equals 0, is 0. Well, let's figure out if that's right. I know from pre-calculus that x to the 2/3 is a power function. That exponent is between 0 and 1. So the graph is going to look like the same graph on the right-hand side that square root of x does, or x to the 1/2, also between 0 and 1. Now the left side, if I figure out if this is going to be an odd or even function, it'll help me determine what's going to happen on the left side. So I plug in negative x, and the 2/3 exponent really means I'm taking the cube root of negative x squared, which then means a cube root of a negative is a negative, it's an odd root. But then if I square it, it's going to be positive. So when I plug in negative x, I end up with the same thing I get as positive when I plug in positive x. So that means I have an even function. My y values are the same regardless of whether x is positive or negative. So now I can tell you that this graph is going to be undefined. The derivative is going to be undefined at x equals 0. So again, we have a calculator fail. And as a reminder, to make that conclusion that your function is, the derivative of your function is undefined at that value, you would have to say, you can't say that there's a cusp there. You have to say that the limit as x approaches 0, well, I'm spicing things up again, I'm using the alternate definition of derivative, but I'm saying that the limit of the difference quotient for the alternate definition of derivative from the left does not equal the limit as x approaches a from the right of the difference quotient for alternate definition. Therefore, f of x is not differentiable at x equals 0.